Let me talk about the last kind of isomers, which are called stereoisomers. Stereoisomers. Now, this kind of isomers are going to be very different from the other kinds of isomers. So I'm going to draw it and then illustrate to you using my modeling kit. So I'm going to start with CH4. CH4 like this, actually like this. Okay, it doesn't matter how you look at it, it's just the CH4 molecule. Okay, just the CH4 molecule. Well, what if I replace one of the hydrogen? Let's say I replace it with a chlorine atom. So I'm going to take off the hydrogen. Okay, so this single bond right here is going to be formed between carbon and chlorine instead of carbon and hydrogen. So they're going to share a pair of electrons, just like how carbon and hydrogen would share a pair of electrons. But now you have the chloromethane molecule, CH3Cl. Now, is there going to be an isomer? Okay, think about this. Is there going to be a structural isomer, positional isomer, functional isomer, or stereoisomer? Well, I haven't explained what is stereoisomer, but I can tell you there's no stereoisomers. No, none. Okay, no stereoisomers. So I'm going to keep going because I want to get to stereoisomers. So let's say I'm going to replace this hydrogen by fluorine. So let me get a fluorine. Let's pretend this is fluorine. So does it matter which hydrogen I take off? Okay, well, these three are equivalent hydrogens. They are exactly the same. Okay, if you don't believe me, just hold up the molecule. Take a look at chlorine. You see the bond angles, they are all the same. The position of these three hydrogen relative to chlorine, they are identical. The chemical environments are identical. So it doesn't matter, right? If I take off this hydrogen and just replace it with fluorine. Okay, now let me ask you again, is it possible to create an isomer? Okay, so now you have CH2ClF. CH2ClF, that's the chemical formula. Okay, can you build an isomer? Well, the answer is no, because, let's say if I take off this bond here, take off this bond, okay, and I just switch the two, does it make a difference? The answer is no, because the fluorine replaces one of the hydrogens, and basically you have the fluorine next to chlorine, but then the other two hydrogens are always going to be next to each other. And you can switch again. Okay, take this off, put it here, right? Take this off. Okay, put this one here, put this one here. Make no difference, right? You still have the two hydrogen next to each other, and then the chlorine and fluorine next to each other. Okay, so no isomer. No isomer. Okay, let's do one more. Let's replace another hydrogen. Doesn't matter. Let's say I'm going to replace it with Br. Okay, so I'm going to get my bromine and orange for bromine. Okay, and I'm going to replace the hydrogen with bromine. Okay, now I'm going to stop and let you look at the molecule. Okay, I'm going to put the molecule. Let me put it here. Okay, I want you to look at the molecule. Hydrogen, bromine, fluorine, and chlorine. Okay, so what I'm going to do is to play a trick on you, okay? Here is CH4. Okay, here's CH4, right? CH4, carbon, 4 hydrogen. Okay, so this time I'm going to make the same substitutions. I'm going to replace a hydrogen with bromine. Okay, I'm going to replace a hydrogen with chlorine. Okay, all right. This time I'm going to replace also a hydrogen with fluorine. Now let me get open over here. Now take a look at these two molecules. Okay, they both have the same formula. Now it's not CHClF, it's CHClFbr. Okay, so it's carbon, hydrogen, chlorine, fluorine, bromine. But pay attention, because carbon form 4 bonds. Okay, so carbon is a central atom. You cannot put the chlorine in the middle and put the carbon here. So there is actually some chemistry of carbon involved. It's organic chemistry. Okay, so let me put the chlorine here. So carbon has to be the central atom. So central atom has to be carbon. But hydrogen forms only 1 bond, chlorine form 1 bond, fluorine form 1 bond, and bromine also form only 1 bond. So they are the outlying atoms. Well, let's go back and look at the two molecules. Well, what do you notice? Okay, well, I'm going to match the 2 bromine and the 2 fluorine, let's say. But what happens to the positions of the hydrogen and chlorine? They don't overlap. You see? They don't overlap. Well, so let's say, all right, so let's mix it up. Okay, doesn't matter. Okay, this time let's say I'm going to match hydrogen and chlorine. Okay, so let's say I'm going to match hydrogen and chlorine. Okay, so hydrogen for hydrogen, chlorine for chlorine. But take a look at the positions of fluorine and bromine. You see, purple, brown, purple, and brown. These are stereoisomers. These are stereoisomers. So they are not structural isomers. They have the same structure, basically carbon forming 4 bonds, like the CH4. So they are not structural isomers. And they are not positional or functional isomers, because they're going to have the same reaction, these two isomers. But they are stereoisomers. Stereo means that the position of the atoms makes the difference, not the structure. The structures are identical, but the position of the atoms is making all the difference. In fact, I want you to get to know a term which is called mirror images. Okay? Well, the idea is, this is my left hand. If you put a left hand in front of a mirror, you're going to see your right hand, right? Your left hand is your right hand in the mirror. I mean, your left hand becomes your right hand in the mirror. Okay? So we call your left hand and right hand mirror images of each other. These two molecules are exactly mirror images of each other. So if you build this molecule and you hold it in front of a mirror, what you see is not the identical molecule of this one. You're actually going to see the mirror image of the molecule that you put in front of the mirror. Okay, of course, you know, a mirror image is virtual. I mean, you cannot touch the virtual mirror image if you actually use a mirror. But pretend that we don't really have a mirror. Okay? You're looking at two different molecules. These are actually isomers of each other. These are two different molecules. And they're different from each other, not because of the chemical formula, but because of the position of the atoms in the structure. So they're mirror images, and they are stereoisomers. Now let me tell you one more thing. Okay, there must be a way that we can tell apart these two isomers, right? They're stereoisomers. How do we do this? Well, we use the RS convention. One of these is going to be the R isomer. The other one is going to be the S isomer. Now, you don't need to know exactly, okay, which one is R, which one is S, doesn't matter. As long as you know that one of them has to be R, and the mirror image is going to be the S isomer. And the reason that we use R and S is because, okay, one of them is the right or right hand, the other one is the left hand. Okay, one of them is R, the other one is called S. There's actually something to it which can tell apart the stereoisomers. The two stereoisomers has different optical activity. Okay, and it's something you can read about, and I'll let you read about. But the idea is that, let's say this one is the R isomer, and if you're going to use a beam of light, okay, so you're going to use actually polarized light. Okay, so let's say you use polarized light. Well, you shoot a beam of polarized light to a sample of the R isomer. The R isomer is actually going to turn the light one of the two directions. So you have polarized light going through the liquid or the sample of one of the isomers, let's say the R isomer. Well, it's going to turn the light clockwise or counterclockwise. So let's say the R isomer is going to turn the polarized light clockwise. Well, actually, this is, let's make it clockwise. Clockwise, right? Okay, so the light goes in and it will turn clockwise. Okay, it will turn clockwise. So what if you replace this sample? Okay, so let's say you don't do this to the R isomer. So let's say you get a sample of the S isomer, okay, and you shoot the same polarized light. Well, the S isomer is going to turn the polarized lights the other way. So instead of clockwise, it will be counterclockwise. So experimentally, this is how we tell apart the stereoisomers, is by the use of polarized light.